this is the demonstration video for the project I've been working on over the past few weeks. Before we get into the architecture of the project and the actual demonstration of using it, let's talk about what the aim of the project actually was. The aim of the project was to use some IoT devices that could be scattered across a campus or a house or a school and then send data collected from these IoT devices to a MongoDB server or any database server and then visualize that data. That could mean seeing how the temperature changes throughout the day, what the average temperature was across the locations, or something like did the AQI cross a certain threshold. Uh, Unfortunately, I did not have access to IoT devices, so we've had to emulate them. But the project still works in the same way, and I am planning on eventually using IoT devices and testing that with the system I've built. But now let's get into the architecture of it and how that's changed over the course of the project. What you're looking at now is the final architecture that we used. This involves the IoT devices, which are currently being emulated on a computer, sending data to an AWS server via an SDK. The clients will generate a JSON, such as this one, which will have the temperature, the humidity, and the AQI. For now, all the actual data is random. So it'll generate a random number between, say, 1 and 200, and then it'll just put that number into the JSON. So after this JSON is generated, the client will make a call to the SDK to post the JSON to the MongoDB server. The SDK will then append the time of sending and the client ID and then send it to an AWS server with a RESTful API on it. The RESTful API will take the JSON, it will give it a unique UUID and then send it through the cloud to the MongoDB server. The MongoDB server will then store all the data from all the different clients, and later you can use a tool inbuilt with MongoDB called MongoDB Atlas Charts to make charts or graphs with the data. For example, this one. This is temperature over time. So you can see as it goes to night, it first increases and then it decreases. Obviously, this is not an actual graph generated by it, it's just for show. And since the data that we have is random, the graphs are much more scattered than what they would actually be if you were to use actual sensors. But what was the architecture we were using before this? Before this, we were using a very similar architecture, except the RESTful API was running on the local host. Now, what does that mean for the project? That just means that every time you wanted every time you wanted to send data to the MongoDB database, you had to make sure the computer was running and the API was running on the computer. Whereas when you're using AWS, it's just running 24/7 and clients can always send data to AWS. Now, this was the second iteration of the architecture, and the first one was quite different. The first one involved the clients sending data to a server running on the local host via a socket. So the server would bind a socket to port 8000 and then the client would connect to it. The server would accept the connection and then spawn a child process and connect the client to that child process. Once the client is connected to the child process, the server goes back to listening and then other clients can connect and then it'll spawn more child processes for those clients. So one child process per client. These child processes would then connect to the RESTful API, which would then connect to MongoDB and then you could visualize the data. However, this had a problem. A lot of this is unnecessary. You don't need this server in the middle. The clients can directly contact the RESTful API. So that's what we ended up doing for future versions of the code. Now, let's get into an actual demonstration of how it works. Okay, let's begin with the demonstration. First, let's look at what's happening on the server side. On the server side, on the server side, I first begin a virtual environment using this directory as a source where I already have all the libraries needed to run the API. I then navigate to the directory with all the code for the API and start the API uh, on localhost at port 8000. The same ones that are specified within the SDK that I am using to post data to this API. The API then just sends this message that this application startup is complete, which tells me that it has started up successfully. Once this is done, I can go back to my local machine and I can then run this command. This is a piece of code that will simply add 25 new entries into the database. Unfortunately, since we don't have IoT devices, as mentioned earlier, the data is random, which is why I can do this. If if this was running actually on an IoT device, I'd only be able to send one piece of data at a time, because if I'd send multiple, it would just be duplicates, because the temperature won't change over such a short time frame. So with the actual IoT device, maybe I'd send one JSON every 10 minutes or every 20 minutes or every hour. However, for demonstration purposes, it's each time I run this, it adds 25 new entries. So let me just run it. As you can see, it adds these 25 new entries. And let's just take a look at this bottom one. We can see the client ID is 1, the time is, well, the current time, and the AQI is 147, the humidity is 55%, and the temperature is 20. Now, let's take a look at what happens on the server side. We can see that it has this code 201 created. That means that it's been created successfully. Additionally, since the UUID was not provided within the JSON, it adds it itself, and it says right here what it is. Just keep the last three numbers in mind, D26. Now, if we go over to MongoDB Compass, an inbuilt tool in MongoDB for viewing the data in a database, go to the last page and scroll all the way down, we can see that right here, D26, the same UUID is there, which means we know that piece of data has successfully made it into the database. Additionally, we can validate that all of the different values are the same. The temperature is 20, the humidity is 55%, and the AQI is 147. The same as here. Okay, now if you recall, there's one last step in the project outline, visualizing the data. We can do that with MongoDB's inbuilt tool, MongoDB Atlas charts. So here we can see that I have all these different charts. You would obviously probably have more if you were to actually build this out and have it running 24/7. Unfortunately, as I'm not paying for it, it only updates every 4 hours, so the data might not be the same as what we've just done. So as you can see here, there are 275 entries, and here it's only saying the total is 250. But it's good enough for this demonstration. We can see here again, as I was just saying, the total number of entries into the database, which here is 250. Here we can also see which client has contributed the most. So let's say if instead of clients you had named your IoT device, for example, for the UCSB campus, if you had one called Harold Frank Hall, and you had another one called say University Center, and then another one for Isla Vista, you could see which IoT device has contributed how many what percentage of the total database is made up of contributions from that. This could help you see things like if you're looking at average temperature, maybe there's a bias towards one side of campus because that that IoT device has simply contributed more more entries than the other ones. Now let's get to the main use case of this, the graphs. This is an example of what the graph for temperature over time would look like. Obviously, since the data is random, it's not an accurate depiction of what the graph would look like if we were to if the same graph were to be made with actual data. However, we can see that it is in a time series. So in this case, it's going from later to earlier. So it's starting here at 5:31 and it's ending here at 1:24. So we can see that the the latest data is on the left and the earliest is on the right. So this could help you visualize how the temperature changes or how the humidity changes. Additionally, you could graph other things like humidity over temperature. So you'd be able to see if there's a link between, as humidity increases, does temperature also increase or does temperature decrease? So it's a very helpful, it can be a very helpful tool in that regard. Now let's see how you can view the code for yourself on GitHub. You can see the code on GitHub. If you want to go through it yourself, you can, but I'll just give a quick overview here. First, there's a README which just briefly explains what each file is and also how you should change it if you plan to use it. This is the code for emulating the IoT device. It makes sensor values using some random numbers, and it also uses the custom built SDK. And it just uses the command within that SDK. So if I now show you the SDK, this is the SDK itself. It's pretty simple. It uses a library called requests to post data. As we can see here, it's using request.post URL, and it's also saying what the JSON equals. And it's getting the URL and also the client ID here from a config file. This config file can be different for each IoT device. Maybe if you wanted one IoT device sending it to one server, one IoT device sending it to another server, you could do that by changing just the URL. And also, if you want each IoT device to have its own client ID, you can change the client ID within this config file. Now let's talk about the API that is running on the cloud. There's this .env file where you can put the connection string for your database as well as the name of your database. This simply defines how the application should start up and shut down. Here we can see the expected JSON format, and if it is not in this format, it'll reject it. So that's quite useful because then you'll get a code saying unprocessable content. So you know that something's gone wrong, you're sending the wrong data. As well as if it gets corrupted, then you don't have erroneous data in your database. Additionally, this is where it's defined that if the ID is not provided, it will generate a UUID using Python's inbuilt UUID library. And finally, in routes.py, this defines the post, the get, and the get specific ID functions. If you can also expand this to include update and delete functions. However, I've not done that as those were not needed for this application. All right, that is everything. So thank you for watching the video. And I will put the link for this GitHub in the description.